Okay, so my name's Alison, and I am with NVIDIA. First of all, I just wanted to say this. I've kind of been practicing, so mi scuso per parlare inglese, ma il mio italiano è crap. So, it actually sounds so much better saying that in Italian. Anyway, so I apologize. So my field is actually artificial intelligence. I went back to university as a mature student, and so I concentrated a lot, more than most people. And what I'm going to do is try and explain who NVIDIA are, why I joined them, why we're all over artificial intelligence, and also just give you some details on our software, hardware, and just a few future plans, basically. So my first year with NVIDIA was basically doing this as a deep learning solutions architect across all of these what we call major verticals. So this is pretty much daily life for the whole of the world. And what that allowed me to do on a consulting role was amass a great deal of applied deep learning understanding. AI permeates everything that both we and all our customers do. And this is across gaming, this is across graphics, virtual reality, augmented reality, simulation, medical, bioinformatics. You can see that here. Even planetary defense. So I wear many hats at NVIDIA now, and this is one of the ones that I'm most proud of. Frontier Development Lab, basically NASA came and said that despite everything that they are capable of doing, that they really needed help on AI. And what we've put together is a program. NVIDIA, we're one of the founding members, but we've put together a program that's, I think, really, really important in today's age, which is cross-collaboration, cross-discipline collaboration. So it's their skill sets in planetary science amongst and shared with skill sets of data scientists and coders like yourselves. This is really cool. Take a look at the website if you get a chance later on. I believe these slides are going to be put up. So essentially, NVIDIA pioneered a new form of computing. And this is a new form of computing that's loved by most of the world's demanding, really demanding users, which is gamers, but also scientists and designers. And this is fueled by this insatiable demand for better and better 3D graphics, for much more realism. And so we evolved the GPU into this computing brain. We invented it. NVIDIA was formed in '93. We invented it and introduced it to the world in 1999. And this sparked the growth of the PC gaming market, which is actually now worth over $1 billion. $100 billion. And gaming is now, we actually just announced this at the latest analyst talks, it's now over 60% of our revenue, despite the fact that we've pretty much turned our focus to AI completely. But really, we continuously reinvent ourselves. We have to do. If you take only one thing from this talk today, it's that adaptability is absolutely key to survival in today's world. You have to be able to just pivot and adapt to what's being done. And coding makes that really, really simple. So we were already working with every car company out there, so it was easy for us to pivot to the self-driving car side because they were already using us for infotainment and for visual, as well as the actual design space. VR as well, we're also doing loads, and obviously GPUs help with this. Our supercomputer capability goes across worldwide, US, Japan, Europe. We are essentially a learning machine ourselves that constantly evolves to essentially solve problems that really matter to the world. And I'm hoping this starts to run yet. So this is sheer physics and mathematics. AI can actually now predict tornadoes, but this is the Oklahoma Finger of God, or EF5. that killed 24 people and injured over 350 other people. But what we're doing here is we're actually simulating it, and we're working with, as it says, Digital Globe and Recon. And the actual, of course, I'm just running a video here, but the actual simulation itself takes upwards of supercomputer capability, something called RVCA, and 8 of them. But Digital Globe and Recon just a few months back demoed this in 3D and in virtual reality. Can you imagine being able to walk through a live tornado simulation? I mean, this is basically the state of play now. But essentially, the year before, what was happening is a similar disruptive force that was actually just starting to build strength. I'm a massive fan of Feynman. I studied a bit of physics and astro myself, so it was a colleague of mine that put this together. This is a Feynman diagram that basically shows the coming together of the GPU, all the data that we're providing as a society, which is key, and the other integral, which is the existing algorithms that we already had. It's really important to understand the definitions. You hear a whole load of hype about AI, and a lot of it, thanks to the movies, you know, is not true. We don't have Terminators yet. But it's really important that you understand. So AI actually incorporates logic and rule-based learning, as well as machine learning. But within machine learning itself is this subset of deep learning. And deep just means it's got more than 2 hidden layers, essentially. There's a few other intricacies, but they are related, but they're definitely not equivalent. And it may be difficult for you at the back to see this, but the timeline here is really important as well. This is not new technology. Basically, it started in 1956 at something called the Dartmouth Conference, where it was Claude Shannon and a group of friends that put together this term, artificial intelligence, and they actually thought that they could probably solve it that summer as well, but you know, here we are now. So have we got any GPU programmers in the audience? So a handful. All right, so for the others, essentially, if you don't know, the GPU, the graphics processing unit, which is NVIDIA's lifeblood, is a co-processor. You still need the CPU, but what you're essentially doing is you're just passing on the actual part of code that can be parallelized. We even have things called OpenACC, where you can literally use Pragma to shunt the parallelized sections of, for example, existing legacy code. And then this leaves and frees up the CPU to take on its typical serial jobs and running OSs, etc. I don't have time to actually go into the intricacies of CUDA, but we've got a stack of resources online. We run a very technical blog in addition to the lay version, called Parallel for All, so take a look at that. So CUDA itself is at the heart of AI, because it's at the heart of our GPUs, and even Intel, if you look at some of the publicity that's going around today, seems to be pivoting that way, which is quite profound, to be honest. But of course it's essential to our hardware, but it's actually you guys and girls in the audience that are essential. So the bonus is, without guys and girls like you, people across industry have no chance whatsoever in harnessing AI. So again, take a further look, take some more courses, and pivot towards this, because AI is now central, even to the people who don't know it yet, to every single business that is out there today. It's probably the most profound thing since the transistor was invented. But essentially, there's a whole lot that can happen, and what you have to realize is that once you've actually got the hang of deep learning or AI or any of the hype terms that you hear, this will actually help you in your job. So it's about getting great coders, getting them into the workplace, but also letting you sort of run free. AI is going to take a lot of the laborious tasks away from us and allow us lots and lots of time to play in sandbox areas, to even break things and do what humans do really well, which is get creative. And when you start getting creative in code, you can do some incredible things. All right, I'm going to do a quick 101 on deep learning for those that actually don't know it. So try and think about here the differences between these two bikes. So that's my first ever Gixxer 750 on the left. And this, of course, is the Ducati Monster. What a computer will basically do is try and translate these images into pixels, into maths, into vectors, and work out the actual differences on a pixel level. And it will actually be able to capture things that we would never have thought about. It will pick up nuances about backgrounds. It will pick up things that, that literally, this is... this is alien eyes that are being used to look at every single problem that humanity currently has. But the problem is, to actually teach an AI system, you have to have a large labeled data set for supervised learning. And as far as I know, we don't yet have a data set like that. I could go and perhaps scrape 1 million pictures of motorbikes off Google, but then I would have to label each one. Now, it was things like Stanford running the ImageNet competition, and the large part of that workload was actually labeling the data. But I'm currently working with Samasource now. Samasource are literally pulling people out of slums in Kenya and India and teaching them how to help us provide these kind of data services like labeling data. It's really quite profound. So basically, you've got things like regression, where you could take, 1 million data points and divide them up into a line. But essentially, drawing that line through the data set, you still need something called a loss function, and this essentially measures how rubbish your system is at making a prediction. And the key is to converge on a solution that's acceptable, that's to a certain level of accuracy, and that depends on the actual applications themselves. Now, the workhorse behind that is gradient descent, and this is essentially what you're looking at. I want to just make a point in the top left there. If you haven't yet had a look at Distill, Chris Olar of Google's work, it's a really cool way of reading papers, and reading research papers is a really great way to actually keep up with this field. So take a look at Distill. So scary maths diagram, but essentially training a neural network is all about trying to find a good minimum on an error surface. Deep learning systems, what they're doing is essentially they are just exploring through huge, huge problem spaces. And as humans, we can't cope with anything more than 3D, maybe 4D. And we're at very, very high dimensional capability here. So we need AI to help us through this, to convert into maths, and we need computers to actually do the computation. And GPUs essentially, they're the workhorse. They take the brunt of it. So basically, deep learning is split between two workloads. You have the computationally intensive training part, where although this is based on the brain itself, you're essentially in a supervised learning setup, feeding in lots and lots of labeled data. Once you've actually got to a situation where you've actually trained and you've reached the accuracy that you want to get, you have something called inference. And inference is basically just doing the forward pass, so you're not doing forward, backward, change the weights, forward, backward, change the weights, forward, backward, and repeating this process. You're just doing the forward pass, so it's very simple, and this is how you can have it deployed on things like a mobile phone. Again, I don't have enough time to go deep into it, but one thing you have to realize is that the world is not static. Images are great. Convolutional neural networks are very, very good at working on static problems like image recognition. But for everything else, which is dynamic, we need recurrent neural networks. So things like speech recognition and pattern recognition in sequence, looking at lots and lots of historical data. So RNNs are really vital because they grasp the structure of data dynamically over time. There were several problems with implementation, but basically this was over 25 years ago, and a guy called Sepp Hochreiter, who was actually the first, at the time, he was the first PhD of Jürgen Schmidhuber, who is now director of the Swiss AI Lab, which I believe is only about an hour away in Lugano, Switzerland. And he solved the problem, and he created something called long short-term memory, which is used throughout every kind of AI dynamic problem that you actually see today. I'm proud to know Sepp. Him and his team are also working on healthcare problems. They're winning things like the Tox 21 challenge, where you can take deep learning and assess how toxic various chemicals are to humans. Take a look at this paper from IDSIA. It's a really good one. Because it gives you an indication of the real understanding of deep learning and how networks represent layer by layer. Now, motorbikes are really cool, but this is way cooler. So this diagram was drawn in 1865 by a guy called Otto Dieters, and it's showing a human cell's body, the soma, in the center there. And all the synapses and dendrites that actually come off this. There is a huge body of work now that is essentially mapping together neuroscience and AI. Capsules has kind of thrown everyone for a loop, because this is Jeff Hinton, considered one of the godfathers of AI, who's actually Bristol-born, but now University of, well, he's in Montreal. And this is his group. And capsules is essentially they're changing the way that we use layers. Instead of just layer, they're putting layers within layers. And this basically allows you to map a whole lot of more information at a cellular level. And again, I don't have time to get into this, but this is the really key thing. Whatever the architecture that you're using, convolutional neural networks, recurrent, etc., the real power comes from these AI systems in the hands of us. There is nothing more powerful than a human being that's assisted or augmented by AI. I prefer the term augmented intelligence than artificial intelligence, because what it does is it brings us to what I consider the next stage. The software is reinforcement learning, or the theory is reinforcement learning. The hardware is both the GPUs that are running this and the CPUs, but also what we're deploying in, which is robotics of varying shapes and forms, both physical and virtual. So everybody heard about AlphaGo, but this was combining, this was reinforcement learning, which combined dynamic programming and also supervised learning. But AlphaGo 0 now doesn't even need that supervised learning part. It made a lot of headlines by saying that it was doing everything itself. Now, when you actually go behind the scenes, it couldn't do anything without coders like you. Whether or not you're working for Google or not, it makes no difference. Without the coders, we still, AI falls flat. So reinforcement learning basically is about learning a policy or the best next move to make. And this is across the board. But the key thing is that AlphaGo 0, whether it's doing it entirely on its own or not, still can't play noughts and crosses. And I don't know what the Italian version of that is, but tic-tac-toe, or it can't play anything other than Go. So what they needed to do, and this was a huge engineering effort, so this is Universe by OpenAI, but DeepMind also have their own DeepMind lab. They needed to provide an environment where the AI agents could actually learn generalization. They could learn to play lots of other different games at the same time. And games engines essentially provide an infinite amount of training data. I don't know if this is going to run. I may have to try and find my mouse. But basically, this is DeepMind's latest work, where, and I actually learned the word parkour. I'd never heard of the word parkour before. But basically, it is being able to do lots and lots of different actions like jumping, running, etc. But it's doing all this all this by itself. It's actually learning to do the running and the jumping without any prior instructions whatsoever. Let me just grab back my and you can take a look at this. So I believe the Tonight Show did a whole thing over in the States because of the way that it was running. It kind of went viral. But essentially, one-shot imitation learning is another thing. So this is where you show a robot how to do something only once. And this, of course, is getting close to how we learn. Maybe you need to see it twice or 3 times, so few-shot learning. But ultimately, we don't need to see something 1,000 times to actually do it. Now, this is actually work from Peter Abeel's group at Berkeley, and this was March 2017. Peter then moved to OpenAI, and he's now left, and along with some other people, he's formed a company called Embodied Intelligence, where he literally wants to work on just this. So apart from that, there is a whole stack of since then, this field has just exploded. I know because I kind of live right in the middle of everything, and it's part of my job to try and cover the research and stay up with the actual progress. And it's drug design, it's astronomy, it's use cases all over the place. I don't have time, as much as I would love to go into every single use case just in healthcare alone. But as it says, there is a plethora. And there's some really impactful work going on by harnessing AI. Take a look at DLTK. This is by Imperial College. And it's just a really great toolkit if you are working in the medical space. Now, I don't know, we kind of had a few issues with the sound. I don't know if you'll be able to hear this. But essentially, this is Nadia by a company called Soul Machines. And this Soul Machines was founded by Mark Sagar, and you may know him. Not his name, but you'll know his work. So he's responsible for Avatar and the technology behind that, and also won Oscars for King Kong. What he basically did was he got Kate Blanchett on board and recorded lots and lots of her dialogue, and they've coupled together with a huge health insurance company in Australia to actually create this avatar that basically individuals can actually use. So the avatar talks to you just the same as Siri would, but you've actually got a face, and she can actually read and understand emotion in voices. And it's an ongoing learning cycle. As I've got the Samsung here, and they've called their assistant Bixby, and it tells you over and over again that it's still learning, and the more I use it, the better it will be. But there we go. Even Unity 3D now has an AI lab. Here's a tip as well to actually look at. Take a look at Dopamine Games, dopamine.games, because they're doing some very, very cool stuff, considering they're actually on the smaller end of games houses. So EA's CEO, Andrew Wilson, was recently talking about the fact of feeding an AI system nearly, say, every acting performance in war films we've ever had before. Feed that into the actual system. How much is that going to improve the game? How much is it going to improve your experience? And putting AI into characters as well. So EA actually just bought the game studio Respawn, and they're responsible for things like Titanfall, for example. So you are going to see, if you play as a Titanfall, you're going to start to see AI in those games very, very shortly. And of course, we're all over this, and we have been for quite a few years. We recently launched Holodeck, simply because we're already doing lots of work in rendering at photorealistic levels. I mentioned before that we're already talking to the car manufacturers, and we've already been working with them for decades. So this is about being able to get together with your collaborators wherever they are in the world, put on a VR headset, and you're there with a full res setup of whatever you're actually working on. And this is essentially a supercar that we actually demoed. But built on the back of this is Isaac. And Isaac is a robotics learning platform that incorporates reinforcement learning as well as any robot that you want to put up there. Now, 2013, I was working with the National Nuclear Laboratory, and we were basically coding a virtual KUKA robot, controlling it with just an Xbox controller. So you can essentially bring anything into this platform, teach it, get a trained system, and then deploy it in a real robot. This is just a screenshot of Isaac in the nursery that we built within the holodeck. And in there, it can actually interact with you and play dominoes and learn from you, all using reinforcement learning. We're only just scraping the surface here. We're only in beta access, but there are so many different opportunities here. And of course, the ultimate robot, which we've been working on for quite a few years, although this is a slightly different problem set because, of course, you're talking about collision avoidance. With robots, it's all about touch and grasp and haptics. But the problem with this is the rest of the world, and that is so complex that we literally had to put together a whole new chipset. So my system seems to be going very slow. Okay, so essentially we put together on various iterations, starting with Drive PX2, and then we went to Xavier on the actual chipset. And this is addressing the ASIC space, application-specific integrated circuits. But then Pegasus is now capable of 320 TOPS. That's trillion operations per second. It's capable of perceiving the world through high res. It's capable of 360-degree surround cameras, localizing the actual vehicle within centimeter accuracy. But essentially, this is such a huge problem space that we want to see the fastest possible adoption of AI technology, and we can't address everything. So we open source the actual deep learning accelerator part of this chipset. We're also right across, and have been for many, many years, the HPC, the high-performance computing scenario. And to prove that, we have over 500 what we call GPU-ready apps. And you can actually go to this link to look at them. And I don't have time to list those 500, but it's across each of those verticals that you saw right at the beginning. So very briefly, I don't know how I'm doing on time, just to give you an indication now of how we enable people. So all our software is free. You simply just go online to developer.nvidia.com. And we work with every single framework. So the frameworks are basically the building blocks. They're the way of literally, almost in some cases in natural language, creating the layers of the neural network that you're going to use in code, in lines of code. There are over 60 different frameworks, but there's probably a top 10. But we work with as many as we possibly can, as there are hours in the day. And I don't really want to recommend, but Cafe 2 is really rocking well at the moment. PyTorch, I personally started in Torch. So PyTorch, of course, is a big favorite of mine. We work with all the teams directly. MXNet, so Apache, they're now part of Apache. And Amazon, widely used. So they're really, really good if you're looking for which framework out of those 60-odd do I start with. There's lots of information online, but basically all our software, as I said, it's free. Just go to developer.nvidia.com and sign up to actually gain from CUDA. And CUDA is what drives everything. This is the programming language for the GPU. And since we actually launched it in 2006, this is really, I know I'm from NVIDIA and this sounds a bit, whatever, but this is exactly why you're seeing a revolution in AI now. It's because people are able to program the GPUs. In addition, we have various other things. So QDNN is CUDA for deep neural networks. It's already at iteration 7, at V7. Nickel, if you know MPI, message passing interface, and parallel programming, this is basically all those collectives for parallel programming in CUDA. And TensorRT, when we spoke about the training side and then the inference side, TensorRT does all the optimizing for you. We've already done all the hard work. If you're using GPUs, download TensorRT, and it's basically going to fuse kernels and speed up every single thing that you've done, because you cannot have a slow operation at inference level. You cannot have a car driving down a road that's going to take a few seconds to make a decision. It has to be as quick as it possibly can. So nickel, as I mentioned, this is all the collectives. Again, just go online. I don't have time to stop into this. Graph analytics is across the board. Many, many, many massive problem sets are just a graph problem. So we've sped all that up with MV Graph and all our teams. Digits is a visualization tool. When I was doing research in university, I was just command line, getting all my input from the very good output that's given from Torch. But then digits came along, and you get to see exactly what's going on in the actual layers. You get a visualization. You get a graphical understanding of the accuracy and how the loss is going. And there's also now a ton of pre-trained models. Data curation in a problem set is actually the majority of the work. It's like 70% of the work. The AI side, you can just pick a pre-trained model, and the job is done. So as I said, TensorRT is for vastly faster inference. Okay. DeepStream is for if you're doing IVA, intelligent video analysis, and a lot of people are. So on the hardware side, of course, for all the software that we have, it has to be alongside the actual the hardware, and we are spending literally billions to actually get the best that we possibly can. So the recent launch, which was Volta, is 21 billion transistors. We are rad limited now. We are right at the edge of what is capable. So what we've had to do is make fine-tunings right down at the instruction set to actually provide even more speed up. And when you're talking about using TensorRT, these are the differences in from just our previous chip, which was Pascal. P100, V100 are just our internal codes. Using, number one, tensor cores, and I'll explain that in a minute, but also with TensorRT. ResNet 50 is probably the hello world now, as something that AlexNet used to be, which is a type of convolutional neural network. And it's a lot bigger, so it creates a lot more demand. So essentially, the tensor core, as I said, is this brand new instruction set. AI is pretty much just matrix, multiplication, and accumulate, or summation. That is really at the heart of it. So what we did is we managed to do the 4x4 multiply plus C simultaneously. And that in itself gives you 12 times the actual throughput already. And the tensor cores are parts, so there's actually 640 of them within the over 5,000 cores that are now on our Volta chips. But all that sounds great, but how do you actually really cope with massive problems? So what we do is we put multiple cards now into one unit. So the DGX family was actually launched back in 2016, and this is 8 high-end cards with our own interconnect, because PCIe just doesn't cut it anymore. So we have our own interconnect called NVLink. But really spectacular now is this use, and I've noticed that there's other talks on containers. So we've containerized all that software. I've spent the hours and hours trying to get all the dependencies together to actually do deep learning work. But we've put it all now inside in containers, optimized containers, and that's optimized to all the major frameworks and onboard DGX. So this animation was put together when we were launching Pascal, and of course it's now Volta. But what's really important is the software is optimized. You simply log in to the system. It can be, of course, multi-user, but it's actually designed to just do tasks very, very quickly. The Pascal is 170 teraflops, so trillion floating point operations, and Volta has just blown that out of the window. So to move on, essentially, this is addressing the simple fact that there are teams of people who are now working on these problems. So it's the ability with containers. And at the moment, it's Docker, but we are looking at all the other use cases, because the HPC will prefer things like Singularity, and Kubernetes is very popular. So we're looking at all that, and we're implementing it as fast as we can. DGX is actually a server So obviously it needs to be rack mounted. If you don't have that capability, you can actually now get a desk side version with Volta. And again, this is actually four cards. It's water cooled, so it's nice and quiet. DGX, the server is not quiet because you've got 8 massive cards doing a lot of work. Alternatively, you can now access Volta right now via Amazon Web Services up in the cloud. And we have something called NGC, or the NVIDIA GPU Cloud, where you have the capability in 3 simple steps to literally sign up. You can either choose to use the cloud or choose to use local compute. Say you've got some of our GeForce cards or you have DGX. And then you simply just pull one of these containers down. We have an entire registry of containers now for all of the frameworks, all of the possible combinations and versions of CUDA and QDNN, etc. But the real key here is that everything's up to date. There's no more, we put out a new version of CUDA or a new version of QDNN, and you then have to go through the whole rigmarole. You'd simply just click on that up-to-date container, and it really just makes life a lot easier. So we build the products for training, things like DGX. We build the products for inferencing, whether that's in the data center, like our Tesla cards. But there is this other part, and that's inference, but also inference at the edge. And this is huge. I mean, this is billions and billions of cameras, billions and billions of edge devices. And we have no idea how big this problem is going to be, but we have to address it now. And this is just some of the actual use cases that we're dealing with on a daily basis now. So, of course, we need an embedded GPU. And we have a credit card-sized GPU called JETSON, now TX2, the version, that is capable of between 1 and 1.5 trillion floating point operations per second in a credit card space. And there's lots and lots of people using this for various use cases. You can actually buy it very cheaply in a dev kit format. It's got loads of I/O. It's got a camera on board. Or if you're an academic, we actually give them away with an entire robotics and embedded teaching kit alongside. So we have these teaching kits that we've worked with NYU and Jan LeCun as well, specifically for deep learning. But Servo City worked with us on these teaching kits with Jet, and you can look online to see. So this entire embedded space, simply because, there's 11,000 of us at NVIDIA, but that's not enough people. So we have to put the entire embedded space online, which means you can get every single piece of information and the hardware purely via the website. And that includes Jetpack. And if I had another hour, that would not be enough to tell you all about the various parts of Jetpack and what it can do. And I think I've only got about 3 minutes left anyway. But essentially, everything that we try to do is so that you can develop and deploy right across the same architecture. That's hardware architecture, with the same software that you've been doing that prototyping on. Okay, so essentially, I want you to know that if there is anything else that you need to understand, we do so much training now that we developed something called the Deep Learning Institute. And this is using IPython or Jupyter notebooks, so you can do hands-on coding on our GPUs in Amazon Web Services right now, but we also work with Microsoft Azure, and our GPUs are in every cloud provider that there is. So this will eventually branch out. We have over 200 different classes. You can go online to that website now and do at least 3 of those for free, where you're doing hands-on coding in a variety of different frameworks. Essentially, you just go on to a setup called Quick Labs, which very, very quickly was actually bought by Google. So Google now own them now. So, of course, Google's entire cloud platform is going to be accessible via Quick Labs. As I said, about 200 different use cases, and there's a few that are actually free for you to have a go at. And there you can actually get down into the actual code and work with code and start to understand it. If you're actually thinking of setting up a startup, then please just do a very quick sign up to NVIDIA's Inception program, where we can actually give you a ton of support and big discounts to hardware and, of course, all the software. And I just want to leave you with the fact that we are hiring massively right now. If you have any kind of deep learning, machine learning skills, or just, you know, the ninja coder, please let me know. Thank you very much for your time. How do I hear it? No? Okay.